à l'université Bishops. Alors, un scientifique de classe exceptionnelle quand on regarde un peu toutes les réalisations qu'il a déjà faites. Alors, donc, il va nous parler d'exoplanètes aujourd'hui. Donc, il est titulaire de la chaire de recherche du Canada sur l'astrophysique des exoplanètes. Alors, M. Rowe a un doctorat de UBC en Colombie-Britannique. Et après ça, il a rejoint la NASA pour faire un postdoc. Alors, ces travaux exceptionnels lui ont valu au moins 2 médailles. Et c'est quelqu'un qui a plus de 200 publications dans son domaine et avec plus de 16 000 lecteurs. Hein. Donc c'est pour nous toute une chance et un honneur d'avoir M. Jason Rowe comme conférencier aujourd'hui. Et je rappelle aussi qu'il est chercheur membre du cartel. Donc, ce qui pour nous est absolument quelque chose de très important. Donc, sans trop tarder, donc, je vais laisser le soin à M. Rowe donc, de commencer sa conférence. Et si vous avez des questions plus tard, on va pouvoir échanger. Merci beaucoup. Jason?
Jason?
Yeah. Okay,
yeah.
You can hear me now?
Yeah, you can start now.
Okay, sorry, I was muted.
It's okay.
Okay, well, thank you very much. I'm happy to give this presentation today. It'll be in English. I'm hoping that over time I'll become more comfortable in French, and I look forward to when I can give this presentation in French. But at the moment, you'll have to put up with me in English. So I'm going to give a brief overview today of my research program at Bishops. It specializes in extrasolar planets, and I think there are some key overlaps between what the cartel does and my own research. And I'm hoping that through this presentation, there's a chance to build stronger collaborations, and I really look forward to that. So I'd like to thank, I have a number of badges on this particular title screen, and the work today is sponsored by the Canada Research Chair Program, Discovery Program, Innovation Program, FRQNT, IREX, which is an institute of Quebec institutions dedicated to exoplanet research. This includes McGill and UDM and Laval, and then funding from the Canadian Space Agency towards studying the potential for doing a Canadian exoplanet mission, potentially in the near term future. And then this is a nice artist description of what I hope that the future will be for exosolar planets, which is that we're finding something that maybe reminds us of somewhat of home, but a little bit different. This particular case, this is the artist's rendition of if you were overlooking an Earth-like planet in front of a cooler star, so there's a star much cooler than the sun, that say put out most of its radiation in the infrared, of what that landscape might look like. So we see kind of yellowish trees, maybe different forms of chlorophyll, different types of scattering of light off the surfaces, but all in all, these are all the telltale signs we'd like to see from habitability. And I'm hoping to move from the artist view into something that's a little more concrete. Maybe within like the next decade, we'll be able to say a very concrete language towards the "Are we alone in the universe?" So since I've arrived at Bishops, our team has grown immensely. Within the exoplanet group right now, we have 5 additional members. I have Dr. Kelsey Hoffman, who is a multi-mission specialist. So she's the one that makes our missions a reality, of doing all the legwork of getting our reports in on time and everything else. She's been involved in our exoplanet satellite as well as large high energy missions as well. I have currently a postdoctoral fellow, James Sikora, we're really lucky to have, who's been doing an immense amount of work on exoplanet mass loss. So this is how atmospheres around planets that might be Earth-like, how they evolve in time and how their atmospheres might change. I have a master's student who's very close to graduation, who has really interesting results on exoplanet refraction that I'll review. I have a master's student, Ben LeBlanc, just finishing his first year, which is embarking on a very interesting project of doing seismology, but on solar system planets, in particular gas giants, like say Saturn or Jupiter, to be able to measure out their interiors. And I have a remote undergraduate student currently at the University of Northern British Columbia, who's been doing a lot of work on Markov chain Monte Carlo and coming up with new methodologies for sampling methods. So for today's talk, I'm going to give you an introduction to exoplanets. I'm going to assume that you know nothing about astronomy and nothing about exoplanets, and then start from there and build up and then show you kind of the really exciting results that have been coming forth. And most of this these days has been towards fulfilling what's called an exoplanet census. These rely on missions such as the NASA Kepler mission and the European Space Agency Gaia mission. And then there's also what's called Qu'est mission, which is the revamped Kepler mission and some observations we obtained of solar system planets and what we're doing with them. And then at the end, I'll spend a bit of time jumping into some space missions, in particular the Canadian side of it, for our goals of trying to get the microsatellite up within, say, the next 5 to 6 years that would have a strong focus on observations of extrasolar planets. So let's start by just putting everything in context. So I'll start with what we all know is common as a group, which is what are the size of planets like in our solar system. And it's important to get this out early because I'm going to use a lot of language where when I refer to planets around distant stars, I like to compare them in mass and radius to planets that are in our own solar system. And we're used to the view that you have rocky planets close to the sun and gaseous planets and ice giants further away. When I start getting into some of the results in the exoplanets, you're going to find that this type of natural order, it's one of many possibilities of planet architectures that we're finding. So if I say a planet is Jupiter in size or Jupiter-like, I'm usually referring to something that's the mass and radius of Jupiter. If I say something that's Earth-sized, I'm really referring to the radius of the Earth. And if it's Earth's mass, likewise. I'll use terminology such as mini Neptune, so something that I think has a large gaseous envelope around it of atmosphere. And so it's like the size of Neptune, but particularly smaller. So you could think of something like the Earth, but with a substantial, say, hydrogen, helium atmosphere embedded around it. And I might use terminology such as super Earth, which is taking something like the Earth and simply scaling it up in both radius and mass. All the work I'm going to be talking about today, because of the young nature of the exoplanet field, where the field's only 20 to 30 years old, means that most of the results that we're talking about are applicable only to the inner solar systems or the inner parts of these distant solar systems. So a reminder, when we think about our solar system, it's a grand scale that's available, where we go all the way up to Neptune at 30 AU astronomical units, so 30 times further away from the sun than the Earth is. But all the results I'm talking about today are really concentrating on this inner part of the solar system. And it's really going to be within the next decade or so that we're going to begin to explore this outer part of the solar system, which is probably very important for understanding the evolution of exoplanets around their distant stars, in particular from things like migration and the overall sculpting of planetary systems. So if I can give you one takeaway message today to walk away with, it's that we now know that planets around distant stars are extremely common. This is a fundamental change in how we think about the universe, and in particular the Milky Way galaxy. Like many of you, when I grew up, we only knew about 8 or 9 planets, right? So we had 9, and then Pluto got demoted down to its minor planet status, and now we have 8 planets. And then since about the late 80s and early 90s, there's been this slow progression of discovery of planets around distant stars to where we're now actually very confident that if you go outside on a clear night and see any star that's up there, that star likely has a system of planets that's in orbit around it. So that's a fundamental shift in our knowledge about planets in the universe itself. So I'm going to spend a bit of time now talking about how we actually discover extrasolar planets. And I want to really highlight the role that Canadians have played in how planets have been discovered and to where we are now today. It's a little bit understated of just the role that Canadians have played in doing this. So one of the easiest methods to understand when finding distant planets is, well, let's just take a telescope, point it at a distant star, and see if we see little glowing balls of light around it. And if we can see them moving, then that must mean that they're planets. And this is now a reality. The movie here on the right is showing observations that are spanning a number of years. And in the center here, where it's all kind of looks like garbage, This is where the bright light from the central star has been removed from using a small from essentially using a chronograph, from blocking out most of the starlight, and then a digital processing afterwards to remove the rest of the artifacts. And what you see in observing over the time scale of years is you can see these dots making their slow progression, each one of them, all four of them here, in progression around their host star. And these are directly imaged planets. This is a very difficult measurement to do. The only reason we can do it for this particular star is because this is a very, very young system. The system's on the order of like 10 million years old, and it's young enough that these planets here are still emitting light as black bodies in the infrared. So this is essentially an infrared image, and this is the glowing embers from the formation of planets around this particular object. This was pioneered by researchers in Canada. This particular image here is provided by imaging from Christian Marois, who has developed chronographic techniques for doing these high contrast imaging that have opened the field towards doing direct imaging of exoplanets. Another common method that's using for discovery of exoplanets is called the rate of velocity method. In this particular case, what's happening is that we have our host star in the middle that's emitting most of the light that you see, and then you have some planet that's in orbit around it. Because this is a gravitational interaction, both bodies will move around the center of mass. Detecting light from the planet is extremely hard, but detecting light from the star is relatively easy. So by obtaining high-resolution spectrums, so taking your light and dividing it up into its individual colors, is we can essentially monitor the Doppler effect of either the star moving towards you or away from you as a reflex motion to the planet going around you. This is also an exceedingly hard to do, because the motion of a star, which can be 100 to 1,000 times more massive than the planet going around it, this motion here is going to be small. For context, with the Earth going around the sun moves at about a few centimeters per second. For the most common detections of planets around, like close-in planets around their host stars, this amplitude can grow to about, the strongest I've seen is about 100 meters per second, with the typical about 100 meter per second scale. So in other words, we're trying to observe the motion of stars at about the same velocity that you take when you walk across the room. The ability to do this was also actually pioneered by Canadians as well. This is a snapshot from an article a number of years back in the Globe and Mail, and this is Gordon Walker, who is a professor at the University of British Columbia, who actually pioneered the technique of getting high-resolution spectrum of stars for the discovery of planets. His genius moment was recognizing that you need to have when you're doing these measurements and you have these large telescopes, the telescopes will kind of flex and bend, and that flexure and bending of the actual telescope is going to add a lot of distortions to the measurements that you want to do. So what Gordon Walker realized is that if he took a cell of gas where he knew that there's absorption features in it and absorption lines, put it into the path of the light, that it gave him a natural reference frame for doing these high precision rate of velocity methods. And it turned out that in about 1988, 1987, him and his group published a series of papers where they had tantalizing evidence of the first discovery of an exosolar planet. In fact, when you go back and look at it now, it's quite clear that they actually did find the first exosolar planet, but because of the odd nature of this particular planet, it was something the size of Jupiter, going around its host star every 3 days, is they were kind of not very sure about it, and it seemed a little too weird. So they were very skeptical of this particular result, and stated in their first papers that maybe this is actually due to some weird stellar physics that they didn't quite understand. The first exosolar planet was officially announced in about 1995 that the community believes, but back in 1988, Gordon Walker's team actually had indeed found the first evidence through rate of velocity of an exosolar planet. And it was through them taking a careful analysis of the data, not fully understanding what they're observing, that kind of led to the first believed study to happen numbers of years later. And then the last method that we'll talk about today is what's called the transit method. And this is the method that I used mostly in my studies in that if you have a star and the orbital inclination is aligned such that the planet moves between you and the host star, that means that once per orbit, the planet's is going to become between you and the line of sight of the star and block a little bit of light. So what this animation shows down at the bottom is this is the brightness of the star seen over time. As the planet moves in front, you see a little bit of dip in brightness. This is also has a Canadian roots in it as well. And around year 2000, David Charbonneau, who is from the Ottawa region, who is now a full professor at Harvard University, recognized that one of the newly discovered planets from the radial velocity method had a strong probability that actually might indeed transit its host star. So he grabbed a small telescope and went out to a parking lot in Cambridge and actually gathered these particular observations that we're seeing here. So this is over time on the x-axis versus the brightness on the y-axis of the brightness of this particular star. And then at some particular time, we see the star dips in brightness and then returns to its original brightness again. And they repeated the measurements a number of days later and saw it again. And this was the first detection of a transiting exosolar planet. And it was very important because up to this time, all the radial velocity discoveries were highly debated in literature of whether they were actually due to planets or if we were actually seeing highly inclined systems and maybe seeing some low mass stars instead. But the discovery of HD 209458b as a transiting planet with also a radial velocity detection just cleared it out. There was no more doubt anymore. We were actually finding planets around distant stars. And these planets are odd. The first discoveries you find are kind of like the tip of the iceberg of what's the easiest to find. And this particular planet has an orbital period of 3.5 days around a star that's like the sun, which says that this particular Jupiter-sized planet has an equilibrium temperature about 1500 Kelvin. So this is something unlike anything that we saw in the solar system. And it's also what kind of was a big surprise at the time for a number of observers of why are we finding these extreme Jupiter-sized planets in orbits around stars where they just weren't expected. This is a measurement of that same system, but instead of using a small telescope in a parking lot, this is what happens when you use the Hubble Space Telescope. So this is a 2.4 meter optical space telescope in orbit around the Earth. And these observations from Tim Brown in 2001. And this is just amazingly beautiful data. This data set's been used for discovery of the first atmosphere around a planet by breaking it up into different light and measuring transit depths, and also doing precision characterization of planets around distant stars. The bulk of the discoveries and to move us from, say, a field where we're doing boutique studies of individual planets around individual stars into turning into more statistics-based so we can understand what are the demographics of exosolar planets and then try to link that back to theories of how do planets form, including does it match with observations that we see of planets in our own solar system. That really has come to fruit due to NASA's Kepler mission. And this is where I did most of my work as a postdoc and a researcher for a number of years. Kepler is a fairly simplistic space mission in that this diagram here on the right, this here on the bottom, this is the spacecraft, and then strapped to it is the instrument, which is a large 1 meter telescope. It was designed to point only at one part of the sky and stay there continuously monitoring for 4 years. It looked at almost 200,000 stars, over 100 square degrees, that's about the size of your hand, held out at arm's length. And with 42 CCDs on board, it gathered observations continuously, almost every 30 minutes, continuously for 4 years to discover transiting exosolar planets. This happened back in March 6, 2009, so just over 10 years ago now. This is the photo of Kepler being launched. So this is on an Atlas rocket. Up here, this is inside the housing, this is where the Kepler spacecraft was contained during launch. So this is the view that we normally look back when we see. I actually went down to watch it in person, and as part of the Kepler team, this is the view that I saw. Due to the changing winds, we got bussed off to this remote site where there was all these trees in our way. Here's the Kepler mission just before launch over here, and there was this old rickety fence that most of the science team was leaning up against. And underneath that, we could actually see alligators that were swimming around. And this fence came pretty close to breaking. So we almost changed the entire exoplanet field in one night, from not only having a beautiful launch, but endangering the entire science team at the same time. This is a picture I took shortly after launch. This is a spacecraft here disappearing beyond the horizon. Here's the booster rockets falling back down to the Earth. And then these dots in the background are actual stars. This is Tau Botus. This is a known exoplanet hosting star in itself. And if you know your star maps, this is the field of view of Kepler on the nighttime sky. So this is Vega. This is the constellation Cygnus of the Northern Cross. So this is a pretty easy part of the sky to pick out in the winter if you know to look for, or sorry, in the summer, if you know to look for things like the summer triangle. So the Kepler data was truly amazing in that the fidelity of the observations has really made the detection of these transiting exoplanets easy. So this is 1 year of Kepler observations. This is one observation essentially every 30 minutes, except for some gaps for communications and orientation of solar panels. But when you look at this particular data, there's a bit of fuzz due to noise, and then by eye you can see that there's these periodic dips that are coming down in the data set. You can line them up and you can see that these dips happen every 45 days. And so by eye, looking at this particular data set from Kepler, you've now discovered your first transiting exosolar planet. We can take one particular part of it. So let's zoom in to one of those transits. So here's a nice, easy to see transit shape. And then again, if you're observant, you'll notice there's another sequence of dips that are occurring there as well. These ones are happening at a much rapid rate, every 0.8 days, so every 20 hours. There's another small dip that you can also see in it. So not only have you discovered one exosolar planet, you've now discovered two exosolar planets from just using your eye. You can take all the observations from the one that's going around very rapidly, you can phase it up. So here's what its transit looks like when you take all the observations and combine them together. And then the depth of this particular transit is a simple geometry, which is going to be related to how big the planet is relative to the host star. So knowing how big the host star is, we deduced that the radius of this planet is about 40% bigger than the Earth. We also went out and got observations with rate of velocity technique to measure the wobble of the host star. And these are well, colored up to make pretty, but the actual observations that we gathered for this particular system. And you can see there's a sinusoidal trend in here that is very periodic with the expected orbital period. And when you combine them together, so the radius and now the mass that you measure from rate of velocities, is you can measure the bulk density of this particular planet. For context, the bulk density of the Earth is about 5 grams per centimeter cubed. For a planet like Jupiter or Saturn, it's about 1 gram per centimeter cubed. So in this case, this particular planet has a Kepler 10b has a density that's actually more consistent with taking Earth-like material and compressing it under an enormous amount of mass that's actually present. So the mass of this planet is going to be on the order of about 5 times the mass of the Earth, compacted into a volume that's only 40% of the Earth. So through self-gravity and compression, we get this larger density. But it's consistent with taking Earth-like material with a little bit more enhancement of iron that we can match this particular bulk density. There's certainly other solutions that are available to this, but at least it gives us some context that we can understand this density in terms of understanding the chemical composition of planets in our solar system. So Kepler was truly amazing. I showed you one particular example of a discovery. After 4 years, Kepler has to 5,000 transiting exosolar planets now, and that has revolutionized the study of exosolar planets and how we understand them. So this particular plot shows on the y-axis the size of planets discovered by Kepler relative to the Earth. So this line here is planets that are the size of the Earth. The size of Neptune are about 4 times the size of the Earth, or the size of Jupiter, or about 10 times the size of the Earth. The x-axis is a measure of how much light or how much energy is being observed by the planet relative to the Earth. So the Earth, orbiting at 1 astronomical unit, will receive 1 unit of flux, and I'm measuring everything relative to that. So the planets on the right part of this diagram are ones that are receiving 10,000 times as much energy compared to the Earth. So these will be planets that will have equilibrium temperatures between 1,000 and 3,000 Kelvin. And then further out on the left part of this diagram are planets that are receiving a little amount of flux relative to the sun. So for instance, these stars down here that are on here, these are the locations of solar system planets. So this is the Earth, there's Venus, there's Mercury, there's Mars, this is Jupiter, and this is Saturn. And in general, we're finding planets that come in a wide range of diversity. This population over here, these are the population of planets known as hot Jupiters. This is similar to the planet HD 209458 that I showed you earlier, would be representative of this particular population. They're the easiest to detect because they're very massive and very large and have very short orbital periods. What's really interesting when you look at this is that these large Jupiter-sized planets, and even planets that are like the size of Neptune, are not incredibly common compared to, say, smaller-like planets. When you get planets that are smaller than Neptune but larger than the Earth, so this particular population here, they're very common. This seems to be one of the most common types of planet that the Milky Way galaxy likes to produce. And it's intriguing in that these planets that sometimes are called mini-Neptunes or super-Earths, we don't have any of these common types of planets in our solar system. So there's a big question of why is that? Why did that happen? Why is it that in our solar system, the largest rocky planet or terrestrial planet is the Earth, and then we jump up to Neptune and Uranus after that in terms of size, and then we get big gaseous envelopes. So where are these planets in our particular solar system? This is a detection diagram, so there's going to be observational bias that's present. There's not many dots on the left part of the diagram because these planets have very long orbital periods, so they're increasingly hard to detect. And then likewise, in the bottom part of the diagram, the number of detections also is decreasing, and this is also due to incompleteness, and that finding small planets and transits is very difficult to do. So this this horizontal line I'm kind of tracing out my mouse is tracing out the incompleteness of our particular detection methods. We totally expect that there'll be planets in this regime, but we just haven't detected them yet. Oops. Sorry about that. That's the weird part about using this. The other interesting thing that you can also notice by eye is that seems to be a gap in the population. This is a very new discovery, only possible from having these large number of discoveries, and that planets seem to be, when they form and evolve, they seem to come in two different classes. You have this particular group up here, so these are the so-called mini-Neptunes, and then you have another class of planets down here, which are now being commonly called as Earth-like or super-Earth-like planets. And there's a division that we can now see that's occurring between these two particular planets, and this division is a function of how much energy the planet receives and how big the planet is. So this is obviously giving you some insights. This is going to be related to the gravity of the planet. So if radius and mass, if they scale nicely, that as we move up in radius, we're increasing in mass. So these planets have more gravity. So they're able to hold on to larger atmospheres. And this is the amount of energy or how hot the atmosphere is going to be. So this is interpreted, this particular gap here, as being as occurring due to the evaporation of atmospheres due to the amount of flux that's received from their host stars. And this is commonly known as photoevaporation. The other part of this diagram that I've highlighted here with the green dashed line is something that's nominally called the Hubble zone. So this Hubble zone here, this is the idea of, you can think of the campfire, for instance. If you're near a campfire, if you get too close to the campfire, you burn your hands. If you get too far away from it, then you get too cold. And there's this nice equilibrium zone where you find it just comfortable. Astronomers define the Hubble zone as being how far away from a planet can you take a planet like the Earth, how far away from a star can you take a planet like the Earth and still have it maintain an Earth-like atmosphere? So if you take the Earth and you move it too close to its host star, you're going to expect that atmosphere to change in reaction to the amount of energy that's receiving. You could have it such that it turns into the runaway greenhouse effect, so you can turn into a planet like Venus, or you can go in the opposite direction and move out, say, towards orbits of Mars, where the atmosphere will freeze out and you won't be able to maintain things like, say, carbon dioxide and oxygen balance more easily into the atmospheres because of the lack of thermal energy that's present. One of the big goals for Kepler was actually trying to detect are planets the size of the Earth common in the habitable zone. And there's not many detections here, there's a few, but there's enough detections here once after accounting for incompletion for us to know that Earth-sized planets are very common in the habitable zones of their host stars. The measurements are kind of uncertain, and they go from 10% of all stars host an Earth-like planet in the habitable zone to like maybe planets host more than one planet like the Earth in the habitable zone. So this number goes from 10% to 200%, and we're still gathering statistics to try to nail that down a bit better. One of the first examples of a habitable zone planet that was found was Kepler 186f. Pretty proud of this one. My postdoc led this particular announcement a number of years back, and it was important at the time because it was the first time we were able to validate an Earth-sized planet in the habitable zone of another star. This is obviously the artist's concept of this particular planet, where we can't image it. We can only see the light from the host star, and then we see how much is blocked out by the planet moving in front of it, and then we try to deduce properties from that. And if you asked an artist, make me a picture of an Earth-like planet around a distant star, they come back with a very pretty looking thing like this. And of course, we made a press announcement about it. It made the front pages of the Globe and Mail. You know it's a Canadian newspaper because there's caribou on the front page, but we also made it above the fold, so we were pretty excited about this. But this comes with a real danger in that by measuring a planet with the transit method, we're only able to know how large the planet is, and from measuring its orbital period, we can measure how far away the host star from the star it is, so we have an idea what, say, its equilibrium temperature, but that's really it. So by having these types of images show up on the front page of the paper, it gives the impression that we're finding planets that we think are indeed Earth 2.0. But that's not the case at all. In fact, without knowledge of the mass of this planet, we don't know if it's some kind of weird iron ball. Maybe it's more like Kepler 10b, where it's enriched in iron and has very high gravity and may not be very intrusive to life. Or maybe it's some kind of planet, and it's more indicative to say something like we see with Mars, with a significantly lost atmosphere, and maybe it's just completely frozen over. So we don't know which of these scenarios Kepler 186f actually falls into. So my research program, especially since I've arrived at Bishop's, has been to try to figure out pathways of how do we actually make planets Earth-like. In order to do this, we'd actually like to understand a number of key concepts about exosolar planets to find out which pathways actually lead towards the formation of Earth-like planets. This includes measurements of atmospheres, radii, temperatures, masses, orbits, planet compositions, and then this last one here, which is, I think we're only starting to get a handle on now, which is the evolution of the planetary systems themselves. So one step back to the basics again. Most of the work that we do with exosolar planets actually derives straight from Kepler's 3 laws. So if you don't remember your introductory astronomy class, I'll just remind you there's 3 laws of Keplerian motion, which are all derived from Newtonian physics, or you can derive from Newtonian physics. The first is that planets move in ellipses. That's nice and easy. And then the second one is that when you move an ellipse, the planet's orbital speed depends on where you are. So this is the focus of the ellipse, where the star would be, and these particular dots are the motion of your planets around it. So if you're in elliptical orbit, you move faster when you're close to the star, and you move slower when you're far away. And then the third law is the harmonic law, in that there is a relationship between the orbital period and the semi-major axis. This is Kepler's third law, or m times p squared equals a cubed. So taking our knowledge of Keplerian motion of planets around host stars, or Newtonian motion, is that if you observe a transit, so this is this concept to give you an idea what's going on, is that here's the host star. This is some planet that we're seeing passing in front of it over time. So over time, we measure the dip in the brightness of the star, and then we get a number of key fundamental observations that come from this, and that using Kepler's 3 laws of planetary motion, we can deduce quite a lot of information about the planetary system. So the first part is, well, how often does it go around? That's the orbital period. And with Kepler's third law, that allows us to deduce what's the semi-major axis, or what's the distance between the star and the planet itself. And if you have knowledge of the host star, then you have an idea of how much energy that planet is receiving. You measure transit times. How often do we see that transit? Does it occur with very specific clockwork, or is some drift for when that transit time actually occurs compared to a perfect orbital period? This will be related to stability and will also be related to gravitational interaction of other planetary systems as well. So this is a very beautiful study, and I'll show you a little bit of work from this, of actually measuring transit time variations to find other planets in the system, and also to another direct way of measuring masses of planets. There's the transit depth. So the transit depth is how much light, this is a simple geometrical factor of how much light from the host star is being blocked off by the planet. So bigger planets will block off more light relative to smaller planets. There's the duration. How long does this transit take to occur? The duration is going to be related to orbital eccentricity. So is it a fast transit or a slow transit? It'll be related to the orbital period itself, and will also be related to the host star itself. If you have a bigger, puffier star, so a more larger star, then the transit duration will be larger. So by measuring the transit duration, we're actually able to measure properties of both the host star and then the orbit of the planet itself. So are they nice circular orbits, or are they have more like comet-like eccentric orbits? There's the egress and ingress. So when you're transiting across the limb of the star itself, we observe that quite nicely. This will be a measurement of the inclination of the system, if we're just grazing towards the bottom limb of the star, or if we have a more central crossing. So we can see the tilt of the system relative to us. And then the last part that makes up this is that the disk of a host star is actually not uniform. There is a stellar opacity effect that's commonly known as limb darkening that makes the limbs of stars look dimmer compared to when we look at the center of the stars. So what this combined together is that you can actually figure out a lot about the orbital makeup of a planet if you have good knowledge of the stellar parameters. So if I know the radius and mass of the planet with high precision, I can back out things like orbital eccentricity. So this is what the state of the art was in about 2016, 2017. What this plot is on the, and astronomers plot everything backwards. I'll tell you that first right away. And this is a bit of a historical glitch. And then on the bottom here, we have effective temperature with cooler stars on the right and hotter stars on the left. So this is effective temperature. And then we measure, we can measure what's called the surface gravity through spectroscopic measurements. And this is a measurement of the gravity at the photosphere of the star, so what you might consider the radius or how big it is. So the surface gravity we measure as log g, and it's simply the mass divided by r squared with the gravitational constant. So the y-axis you can think of being the puffiness of a star. So large stars, very large stars will be at the top of this diagram, and compact stars will be at the bottom of this particular diagram. And then we have temperature as the other measurement. So if you can, so this was about the state of the art back in about 2016. For the Kepler sample, we had a measurement uncertainty of how big we thought the stars were to about 30 to 50%. So it was actually quite poor. And while there were studies of using this large sample of measuring eccentricities, it was actually quite difficult. With the launch of the Gaia mission and the release of its data, that has changed dramatically. Gaia, as a European Space Agency, its mission was to measure parallaxes to billions of stars in the Milky Way galaxies. Not hundreds, not thousands, but billions. And the parallax measurements are so precise that we can measure for some nearby stars to like 1 part in a million. So parallax is a direct indicator of distance. If I tell you how far a star away is from you, together with measurements of its temperature, is you can actually figure out its radius very accurately because stars act as black bodies. So this is what it looked like in 2016 or 2017, and then this is how the picture cleared up with Gaia. And I purposely put the surprise Pikachu picture here because change in, say, the fuzziness or blobbiness of this particular diagram, especially from the astronomer's view, is spectacular. And we went from measurement uncertainties from about 30% all the way down to 5%. And that change in how well we can actually measure the radius of a star has given us increased knowledge of how large the planets are themselves. So we have precise measurements of radii of planets, but we can also do things like measure eccentricity. So eccentricity is a measurement of how circular an orbit is. And if you have an eccentricity of 0, the orbit is perfectly circular. If you have an eccentricity of 1, then the orbit is essentially a line. And using, I did this study before we had Gaia, but if you do it now, you get essentially better results. But what we showed is that in this gray particular line here, this is what the eccentricity distribution of transiting planets are. In other words, most planets that we are discovering have very circular orbits, and that we're finding systems that look very much like our solar system. It's not planets zigging off in every direction whatsoever and high eccentricity, they look very organized and very regulated and have orbits that seem to be very circular. There are examples of the extremes, but for the most case, these solar systems that we're finding look very much like our own, and in some cases just scaled down versions. We also did a very nice study of using transit timing variations. So this is measuring, is the orbital period constant with time? And this is done by measuring when a transit occurs and asking if it occurs earlier or later with time. So this particular diagram here shows you 3 planets in one system that we measured. This is Kepler 138b, D, and C. And what this diagram shows on the bottom, on the x-axis is time, and on the y-axis is a measurement of if the transits are occurring earlier or later. And for many cases here, you can see that the observed minus calculated, so the difference is actually anti-correlated from different planets. This is a clear sign that we're seeing gravitational interactions between different planets in the system. To give you an idea of how this works is I will set up a planetary system. This is one that we know exists. On the left axis here, I will populate the system with planets that have a mass, have planet-like masses. And then on the right, I'm going to set up the simulation to have masses that are essentially the mass of, say, something like a star. So I run the simulation, and the planetary system, when we have planet masses, stays relatively stable. And this system over here, where there's way too much mass presence, quickly tears itself apart and things get scattered all over the place. But by tuning how massive the planets are, is you can then try to reproduce these measured transit timing variations, and then it allows you to measure the masses of the individual planets using transit timing variations. So a study we did on this Kepler 138 system, we were for the first time able to measure masses of planets that were both, say, Earth-sized. So Kepler 138c has a mass that's twice the size of the Earth and about 20% larger, and 138d has a mass that's actually much less than the Earth. So this is a particular case where both planets have the same radius, but they have very different masses. So we think this one here, where the density is half the Earth, is some small rocky-like core that has a large embedded atmosphere around it. This particular planet, Kepler 138c, we interpret as being something that's, say, scaled up version of the Earth and maybe has some thin but high molecular weight atmosphere around it. And then Kepler 138d was remarkable, and that was the first time we were able to actually measure the mass and radius of a planet that was actually similar to Mars. And it's very consistent with the overall density of Mars itself as well. This gives us kind of the state of the art at the time. This is the mass on the x-axis versus the radius on the y-axis. Here's Earth, Venus, Mars, and Mercury. These were the measurements of masses and radii previous to our study, and then these orange dots here is what we were able to do as part of our study. So these were really the first time we were getting masses and radii of measurements of planets that indeed we think are now beginning to sample terrestrial-like planets in distant systems. So I'm going to skip ahead a little bit. and then concentrate a little bit more on the demographics. So far I've talked about orbits of planets, which seem to be relatively behaved. We're beginning to measure masses of large and radii of number of planets, so that we're getting to densities. But the next thing we want to be able to understand is atmospheres of planets and the evolution of those atmospheres. So this red line here is the radius gap that I pointed out earlier. So these are these small Earth-like planets, and these are these larger Neptune-like planets. And this red line is kind of just measuring this particular gap that seems to appear between them. If I now take this diagram, and what I'm going to do is I'm going to break it up into a number of temporal zones. So these are the hottest planets in red, and I'm going to take all the coolest planets here in blue, and I'm just going to bin up all the planets inside each of these color bins, and I'm going to apply correction factors for incompleteness, and I'm going to plot their occurrence rates. So the bottom axis here is the radius of the planet, and then the y-axis is how many planets we're finding per star, and including all the incompleteness corrections that go with it. For planets that are very close to their host star, this is this red sample, is it peaks around planets that have the radius of the Earth. Whereas when you go further away, so the planets that are much further away from their host star, these are ones that are similar to the amount of flux that the Earth receives, is that distribution changes, and that it peaks at planets that are about 1.2 to 1.4 times the radius of the Earth. So what we're interpreting here is that we believe that most planets actually form with large substantial atmospheres, and that over time they are sculpted, especially when you put them very close to their host star, they become sculpted, and many of them lose their atmospheres due to the impact of how much energy those planetary systems receive. In terms of timescales, the average age of a planetary system here is on the order of 5 billion years, so 5 gigayears. So this is a pretty much equilibrium state of where we're finding these particular distributions. That means that planets, we believe that planets that are like Earth-sized or a little bit, or Earth mass and a little bit larger, we're finding strong evidence that they form with massive atmospheres. We believe this is true from the formation of the solar system as well, and that this is the birth population of Earth-like planets. And that you need some other mechanism, say like major collisions with moons, and be able to evolve these initial hydrogen helium rich atmospheres and then transform them into the type of atmospheres that we have around the Earth today. The study is being conducted by my postdoc, and he's put together this really pretty animation that what's going to happen is that you're going to get a line that starts in, and this is flipped from my diagram. So we're going to start far away from the host star, and then this line is going to scan through the planetary systems till we get very close to the host stars. And then the bottom axis is plotting this occurrence rate. So what we're seeing is that far away from the host star, most planets have large radii. And then as you get closer and closer in, the number of large planets becomes less common, and the number of small planets become more common. We believe this is due to this photoevaporation effect, and that planets with substantial atmospheres that somehow make it close into their host star have their atmospheres significantly radiated away and escape, and then what's left over are these rocky cores, so the inner remnants of the initial planet formation mechanism. We can take this another step forward, and that because we have these transit measurements, is we can design experiments that take advantage of effects that you will see. This is an actual picture of Venus transiting in front of the sun in its limb. So this is the dark silhouetted part of it, and you notice that there's this little beam of light on the outside, and we're actually seeing light refracting through the atmosphere of Venus. So we know Venus has an atmosphere just from these observations alone. The amount of light that you see allows you to actually measure properties of Venus's atmosphere. So you could take this particular effect, and now we can apply it to distant extrasolar planets by looking for these particular refraction effects. This is Titan. So this is a planet around Saturn, and this animation is going to show Titan moving in front of two background stars. So this is just happens that at a particular moment in time, we could point a large 200-inch telescope observed Titan, and when you watch the distant stars disappear behind Titan, if you look along the limb of Titan, you'll see that there's these two little blips of light that trace it. This is the light that's refracting through the atmosphere of Titan. So by measuring this refraction effect, you can figure out the atmosphere, in particular the mean molecular weight of this atmosphere, and that the temperature plus the mean molecular weight is going to be a measurement of the scattering of light and the refraction of light as it goes through the upper atmosphere. So my master's student, Derek Nazant, came up with this neat idea, and that because this effect is very hard to measure, and we can't measure it for any individual planetary system, is he realized that if you take all the planetary systems that we have from Kepler and then co-add all their transits together, so he scales them such they have all the same durations and co-adds them together, is he can attempt to actually try to measure this refraction effect. So what he did is that he took the sample of this Neptune, mini Neptune size-like planets, the ones where we expect to see a significant atmosphere, and measured the average out-of-transit brightness, and then co-added them all together. So what this figure shows here is this is the x-axis you can think of as time. It's phase here, so this is the dark part of the diagram is when a transit occurs, so ignore the data in there, it's kind of disrupted. And this is the out-of-transit data. So if we're looking for this refraction effect, we're going to observe it when it's crossing the limb, so just before the main transit occurs. So the blue dots here are measurements with 1 sigma errors based on combining thousands of planetary transits together. So we're measuring now at the 1 part per million level in the change of light that we're seeing. And the dots on the background is different models that he's computed for the strength of the refraction effect depending on the mean molecular weight of the atmosphere that's present. So this is for something that's, say, super Earth, so something would have a mass of, say, 4 or 5 times the mass of the Earth, with an atmosphere that's around 10 grams per mole, so still less dense than the Earth's atmosphere, compared to something, say, 2 grams per mole, so something that's dominated completely by hydrogen. And what he's finding is that we rule out to high significance that these planetary atmospheres are dominated by hydrogen. This is probably okay. It means that things like a hydrogen-helium, where you introduce much more amounts of helium, is probably the right mixture for explaining these volatile, rich atmospheres if they do indeed exist. So the last thing I'm going to show you from my group is observations of solar system planets that we've observed from what's called NASA's K2 mission. So the NASA mission, what was successful is that after 4 years of operations, these black disc hockey puck looking things on here, these are the reaction wheels on board for stabilizing the spacecraft, and after 4 years they broke. And it changed the way the mission worked, and that we can no longer look at the Kepler field of view. But smart engineers figured out that by having 2 remaining reaction wheels and spinning them against solar pressure, so this is light hitting off the solar panels and then adding momentum to the spacecraft, by spinning the wheel reactions against solar pressure, we could actually balance the spacecraft to observe along the ecliptic. So if you're observing along the ecliptic, you can observe planets like Neptune. So we proposed to use this K2 mission to actually get observations of Neptune. And the reasoning for this is that we want to figure out what the interior structure of Neptune is actually like. Is there, for instance, a core that exists in the middle that's a key prediction of planetary formation models, where you have some initial rocky core that builds up to a significant mass that then allows for the accretion of ices and gases to form the ice giants like we see today. So with K2, we observe towards one patch of the sky, and this is Neptune speeding through our field of view. We see it moving because the Earth is in orbit around the sun. So this is essentially a parallax motion. And you can see one of its moons, Triton, in observations around Neptune. If you look careful, there's another moon that's in orbit around Neptune as well. But these measurements allowed us to, and it lasted for about almost 80 days, is we were to take these measurements and measure how the brightness of Neptune changed over time. So we had 80 days of photometry. This bottom plot here shows you if you observe Neptune continuously, what happens. Most of these wiggles that you're seeing here is because Neptune spins around and has an orbital period around 16 hours. And this is the rotation of Neptune and the formation and dissipation in the clouds of the atmosphere of Neptune itself. What we were trying to do was actually see if Neptune itself is actually pulsating. If you were to take these types of measurements for something like the sun, is you would actually see that the sun does actually have this oscillation pattern present because the outer atmosphere of the sun is actually convective. So looking at a frequency analysis of our observations is that this is the rotate, so this is in microhertz. If you're not familiar with that, this is hours, and down here is on the order of minutes versus its power density. This is because we're observing in reflected light. This is light from the sun. You can actually see the oscillation patterns from the sun itself. You can see the rotation from Neptune itself. And the hope was that maybe we would see excess power somewhere in this range, which would be the natural oscillation modes for Neptune. Unfortunately, we didn't see them, but the strict upper limits will be important for future designs of instrumentation to try, because we really wanted to get down to about the part per million scale, and we didn't quite get there with this particular experiment. So the last thing I'll talk about very briefly, and then I'm happy to take any questions that you like, is that one of the big projects we're moving forward with at Bishop's is developing a microsatellite mission, and this has been supported with studies from the Canadian Space Agency and is a joint study between Bishop's University and Western University, previously known as University of Western Ontario, to build a small payload with a optical and infrared telescope on board that would have a diameter of 15 centimeters to be able to observe the transits of exoplanets to see as light goes along the limb of it. Are we seeing, for instance, light pass through with some scattering? Is there no atmosphere or very high density atmosphere present? Or maybe if there's something like clouds present. So the concept here is that as a function of wavelength, we want to measure how large is the planet. And depending what's in the atmosphere, if the atmosphere is very opaque at a very specific wavelength, the planet will appear larger. And from there, we're hoping to be able to measure things like Rayleigh scattering in the atmospheres in particular to deduce the overall population of extrasolar planets. This is a concept of our optical design, which is based on heritage from the MOST mission back in 2003. But we're looking for a launch date around 2025, probably 2026 now with all the COVID delays. We're looking for a low Earth orbit. It'll probably be on the order of about 600 kilometers in a sun-synchronous orbit with a 15-centimeter optical telescope that will target the U and I band, maybe J band, with good integration times to be able to measure transit depths very precisely and to do this transit spectroscopy. So it's as a function of wavelength to be able to measure the transit depth, so the radius of the planet measured to a star, and see if we can actually see this change as a function of wavelength. The dots here are actual measurements of a planet known as HD 189733, done with the Hubble Space Telescope. So the concept, we know it exists. And so now we're going to try to replicate this moving forward with a small Canadian satellite to actually target this large number of planets that we know exist to be able to measure the atmospheric properties through Rayleigh scattering of the properties of the atmospheres now in this particular range of planets. And we're pretty sure we can do that. So I'll stop there. Like I said, exoplanets is an immense field. It's pretty exciting, everything that's going on these days. I'll just give you a couple bullet points to walk away with. There's more planets than stars in the Milky Way galaxy. Earth-sized planets are extremely common, much more common than, say, large Jupiter-sized planets. There's this really neat radius gap that has now been observed, that we're actually able to now observe how atmospheres evolve under the influence of stellar radiation. And we're now making significant progress in a couple of years, especially on the Canadian side with the small exoplanet mission that I'm the PI on. There's one I didn't talk about at all. It's called Castor, which is the Canadian flagship with an exoplanet component. And then something that can be in its own talk all by itself is the James Webb Space Telescope, of using all these techniques I talked about in this endeavor to try to search for, is there actually life in the universe itself? So I'll stop there. If you have any questions, feel free to ask. Because I'm nearby as well, feel free to email me, and I'm more than happy to talk with everybody, and especially, like I said, maybe you find some interest here and we can find future collaborations. So thank you.
Merci beaucoup, Jason. Donc, c'est la période des questions. Je vois que Norm est déjà prêt. Oui, Norm.
Hi, Jason. Fascinating talk. Thank you very much. I'm a professor, adjunct professor here at the department. I'm actually a Bishop's graduate. Don't ask me what year. I was just wondering, when you had some technical questions, when you deduce the installation of a planet, when you talk about the installation of a planet, do you deduce that from the orbital parameters you get, or do you actually, for some planets, somehow measure the installation from the temperature of the planet or something?
Yeah, so in the bulk majority of cases, we're deducing it from the orbital period and the mass of the planet. So we take a simple application of Kepler's third law to measure the semi-major axis, and then given that mean distance, we then know how much flux per area hits the planetary surface. So we measure that relative to how much energy hits the top of the Earth's atmosphere. That can be very different for, say, what the surface temperature is, which will obviously depend on things like the albedo and cloud properties. But this is a simple measurement of how much energy is hitting the absolute top part of the atmosphere relative to what we receive for the Earth.
Okay, and which leads me to my second question. But the resolution that can be attained, let's say even by a satellite telescope, there must be, I mean, there's limitations on the size of the optics and the size of the telescope that you can have even for something like the Kepler telescope. So I'm wondering just what kind of resolutions one can be attained, or do you improve your resolutions by integrating over time? I think you suggested that at one point. What kind of as you look at further and further stars, there must be a come a time where you'll no longer have sufficient resolution to get the statistics for those stars?
Yeah, so you get so one thing is that you can, because planets they come around on a very periodic basis, is you can observe multiple transits and then co-add them together, and we certainly do that. It becomes really difficult for like planets like the Earth because it only transits once per year. So if you need to observe, say, 10 transits to get to the right singleton noise with small optics, it's a 10-year experiment. Yeah, you know, I didn't show this plot, but this is one that we show for our small sat. That this is we're considering small optics, 15 centimeters, but you can make up for the small optics by co-adding many transits together. So this is an example with 10 transits put together, and then this would be the retrieved signal from our simulations of the planetary radius versus wavelength. In particular, this measurement over here, which would be clear evidence of scattering in the atmospheres. To blow you away, when the JWST instrument launches, for James Webb, in particular the nearest instrument, which is the Canadian contribution, this is a simulation now going from, in microns, from the red part of the visual spectrum all the way out to the near infrared. This is a type of spectrum we expect to see with James Webb, with the same particular techniques. And most of these wiggles you see on here, so this is mostly carbon monoxide and water that is producing this particular signal. Believe this is sodium that happens here, but most of this is carbon monoxide that we would be able to deduce in the atmosphere from these types of measurements.
Okay, thank you very much.
Est-ce qu'il y a d'autres questions?
Yeah, Jason?
Yes.
Yes, Nicholas here. I wanted to know, like, what made you focus primarily on the transit method compared to the other two?
Yeah, so the main reason for the transit method has been the efficiency of the surveys that we can do. When you try to do like a rate of velocity survey, you're targeting one particular system at a time. And then with the rate of velocity measurement, you also have to observe a large amount of the orbital phase. So it's a large amount of resources that's necessary. So you need very dedicated telescope time and dedicated instrumentation for doing it. And from my perspective in the research program that I'm able to do, I just can't support that. But with a transit survey, it's extremely efficient because you only need to observe a few hours for when the transit occurs. You have the ability to co-add together, and then because it's transiting, you know the inclination of the system. You know that it's directly towards you. So that additional bit of information allows you to pull out things like masses much easier because there's no ambiguity of the projected rate of velocity signal coming towards you. So combined with the efficiency and the large amount of additional information you get from a transit, it's a nice way of attacking the problem statistically. And it's one of the things I've really tried to focus on through developing my program is to get away from boutique studies of an individual system and really try to focus on the more overall statistics of what the exoplanet population is.
And do you see, like in your specific field, like many more teams now and then working at the transit method, or are still many teams still working at the other two methods?
So most people have their foot in both teams. So I certainly work with teams that do the rate of velocity method as well. But like even this week, there's a full conference going on dedicated to observations of transiting extrasolar planets. That's multiple days. So it's there's an immense amount of information that's coming from these particular surveys. And there is at least 2 more space missions that are planned or that are ongoing and planned. There's the TESS satellite, which was launched by NASA 3 years ago, that is right now still operating and doing a very all-sky survey of transiting extrasolar planets. And then the European Space Agency, for about 2030-ish, beyond that, has what's called the Plato mission, which is kind of like Kepler on steroids, of also trying to do that. Trying to do also a Kepler-like transit survey as well. So it's you can't beat the efficiency of this type of methodology.
Cool, thanks.
Okay. Est-ce qu'il y a d'autres questions? Jason, I'm wondering, until now, how many exoplanets are discovered? About how many exoplanets are discovered until now?
Yeah, so if you were to go look at the current statistics, I think right now, if I were to dig it up, it'd be on the order of 5,000 to 6,000 are known.
Oh.
Yeah, and so that's why you don't see the front page of a newspaper anymore, like astronomers have found a new planet. Unless they something special about it, because they're everywhere.
And among those planets, how many are considered as potential candidates for life?
It's a great question, and it's one that's really hard to answer. So this is just the Kepler sample in terms of its demographics. So this green line here, so this is Venus, and this is Earth. If you would like to think that to have life, if a planet has to be Earth-like as much as possible, so it has the same gravity, has the same atmosphere that it can maintain, that means that only the planets that are kind of around this area where I'm hovering my mouse around, these would be the ones that are could potentially host life, if that's your criteria. The good news is that if you do the statistics of how common are, because this is only the ones that we know about, right? So only a handful that we know about, maybe about 10 are in this regime from all the sampling that we've done are in this regime. But if you take that 10 and then apply all the correction factors, it turns out that on the order of almost every sun-like star appears to have an Earth-sized planet in the habitable zone in orbit around it as well. So if life is naturally forms on Earth-sized or Earth-like planets, let's just for the sake of matter say that all Earth-like planets form life, it's just a natural consequence of planet formation, then that says that life must be common throughout the universe. But this is only looking at a biological scale. There's obviously, we could probably have a whole nother seminar talking about are the conditions here even possible for life to form, right? There was even the discovery a couple weeks ago, refuted discovery about the detection of phosphine on Venus and whether Venus could actually host some type of biology. So which of these planets could actually host life, I think, is a grand open question. But certainly the low-hanging fruit at the moment is attempting to go after these types of planets and to try to do observations, especially with this transit spectroscopy method, to look for what are called biosignatures. So do I see traces, do I see in the spectrum large amounts of oxygen being present? And that if I told you there was this distant planet and its atmospheric composition was identical to what we observe in the Earth, you might conclude that the only way to produce that type of composition is to have biology present, because the only reason we have large amounts of oxygen in our atmosphere is because of biology.
Yeah.
And I'm sure there'll be a geologist that will put their hand up and correct me and say, well, I can figure out ways with incoming UV flux of releasing lots of oxygen into the atmosphere as well from rocks. So it's an interesting discussion, especially I think within the next 10 years, when I'm almost certain the first evidence of biosignatures will be reported. And then as a community, it's coming together to discuss whether or not it indeed is a biosignature or if it's some sort of natural chemistry or geology that's present in these distant worlds.
Excellent. Est-ce qu'il y a d'autres questions, commentaires? Okay, Jason, we want to thank you for this nice talk. It was very interesting. Thank you very much.
Oh, you're welcome.
Okay, merci beaucoup à vous tous.
Thanks, Jason.
Thank you.